Hi, I'm going to keep going with this series of lectures, and this lecture will be dedicated to how we detect ions in the atom probe and then what we can learn from looking at the detector space. And again, some of the bits and bobs that are in there were taken from colleagues, including François Vurpillot, but also others. Like for all the other lectures, I can only encourage you to go back to some of the textbooks on these aspects. I think we did a decent job in the book we wrote about 10 years ago with Mike Moody and Julie Kearney. And also, I think it's quite useful to go into the local electrode atom probe tomography from Dave Larson and colleagues from Kameka. Finally, some of these aspects are well covered also, especially on the detection in the atom probe tomography book from the French group, Williams Lefebvre and François Vurpillot and Xavier Sauvage. To get back to how atom probe works, so we have this sharp specimen, radius below 100 nanometers, cooled down to 80K. We apply the high voltage, the surface atoms transform into ions, are projected away from the specimen surface. Because of the high curvature of the specimen tip, the ions are projected highly divergently, so there's a high magnification to this projection. We collect these ions onto a position-sensitive detector, and that's the point of this one lecture, so I'll get back to this in quite a lot of details. And we trigger the departure of these ions either through laser pulsing or more traditionally through high voltage pulsing. This allows us to measure the time of flight between the time of flight of the ions between the pulse and an event on the detector. And then this allows us to build this three-dimensional reconstruction, 3D point cloud, where each point is one ion that was detected and identified. Let's go to some experimental considerations with respect to this detector and detection of multiple hits in particular. So during a run, you can always see that there is these multiple events that is quoted, and also when you're looking at your data afterwards. So this was in IVAS, in AP Suite, the data is also available. So this means that we've collected quite a lot of ions coming on where not only a single ion was detected, emitted by one pulse, but multiple ions were collected. What that means is that you have two ions that have flown, struck the detector, and generated these different signals. Again, on the LEAP 5000 XS, we have three lines looking more or less like this, and the detector efficiency is expected to be about 80%. But how close can two ions be before one of them might actually be lost? Because I've told you we have to generate these signals, and then the signals must travel along the lines, and then we collect these signals, and we need to attribute to each ion a set of, in that case, normally 6 signals. But if the two ions strike very close on the detector, there might not be enough electrons to trigger, or it's just going to be one big electron cloud, so there might actually be issues. And I've mentioned before that when an ion strikes, the microchannel plates need to recharge. So if one ion strikes the detector at that position, and a second ion comes exactly at that position afterwards, after a very short amount of time, can the detector detect the second ion? So Zirong Peng, when she was a PhD student working with us here at MPRE up to a few years ago, had quite a lot of multiple hits in the analysis of a tungsten carbide that she was working on. And so she looked at the number of counts and looking at how many counts she would get after a certain delay on these multiple events. And actually she could see that there was a significant drop in the number of events for ions that were very closely separated in time by less than 3 nanoseconds. So after one ion has struck the detector, there is a sort of a gray region here where it gets very difficult for the detector to actually find out that a second ion has arrived. Now, if we look specifically at the ions coming in short proximity in time and look where they are located on the detector, we find a pattern that initially was rather puzzling, but we find that it forms a pattern of a cross with this additional line at 45 degrees. And this resembles the organization of the lines of the delay line detector, with two lines at 90 degrees and a third one at 45 degrees. And this indicates that when the signals are overlapping too much with each other, then there's a higher likelihood that one of the signals gets lost. But this varies with time because the signals propagate along the lines. So as we look at different times after the impact, we see that this pattern is changing, and it's changing in non-trivial ways because of the way the signals travel along the lines and where the overlap between the different signals from the different ions arriving successively on the detector can overlap. Multiple hits are typically not homogeneously distributed within a dataset. If we take even something like pure tungsten, for example, in that case, we see that the most of the multiple hits arrive along zone lines and the poles, and also at crystalline feature, microstructural features like grain boundaries. And this is due to the field evaporation process, specifically at these locations at the specimen surface, that prevents good field evaporation to take place, and atoms tend to, as soon as one atom leaves the surface, the neighbors left behind are not very happy and they leave during the same pulse. And it can be seen as an issue, but it's also an opportunity to dig deeper into the data. And we did some work, for example, at looking at the mass spectra for the ions coming not only on single hits, but also on double hits, triple hits, quadruple hits, and so on and so forth. And this gave us an opportunity to actually increase the signal to background ratio, because most of the carbon, for example, in this high strength, low alloy steel was coming on multiple hits. And so we could actually retrieve some signal out of the background. Another reason that can produce multiple hits is when a molecular ion gets emitted following, for example, one single laser pulse. This molecular ion is typically metastable, and under the influence of the intense electric field, plus the fact that it's actually metastable, these molecular ions can just dissociate. And this will mean that for one ion that was emitted, multiple ions will strike the detector. Some of them might get lost, but often both of them will get detected. There can be very complex processes in this dissociation process that take place with some exchange of energy between the ions, but also typically when you have two positive charges in very close proximity, the Coulomb force is going to push them away from each other, so they might actually not follow exactly the same trajectories. But these ions, we can detect where they land, for example, the distance between them and the time between them. And if we, for example, look at this very specific types of correlation histograms, which were first introduced by David Saxey, and I invite you to read his paper, where we plot on the x-axis the mass of one of the ions coming as part of a multiple event, and on the y-axis the mass of the other ions coming as part of this event. And so when we have, for example, emitting in this analysis of tungsten carbide that Zhirong Peng was pushing, if we can have, for example, here tungsten and carbon being detected together, and it can be carbon in the 2+ charge state or the 1+ charge state, and tungsten in the 3+ charge state or 2+ charge states, and we see these hot spots as being locations of when often tungsten and carbon are coming together. And most often these hotspots appear along vertical lines or horizontal lines corresponding to typically to delays in the field evaporation process or exchanges of energy. But here you also have these lines appearing that go towards the bottom right. And these correspond to some tracks where there was an exchange in energy between the ions, and going from one end to the other, we can retrieve what was the parent ion and the daughter ions, and we can actually make use of this information to better understand the field evaporation behavior of some of these ions. I invite you to dig deeper into these types of processes, for example, looking at the paper from David Saxey, where he introduced these dissociation plots or correlation histograms. Some of the works that Zhirong did, where she actually looked at this detection of multiple events and the way they're distributed on the detector in time and space. On the dissociation of molecular ions, we did quite a lot of work a few years ago in gallium nitride, for example. This happens quite a lot. And also some work on trying to explain why when an atom leaves the surface, the others are going to follow closely afterwards. Let's go back to the detector map and try to better understand the pattern that is formed on the detector. If I look back at this detector map, I can see a pattern of so-called poles, these low impact density regions that are joined by lines, and these lines are zone lines, and they reflect the symmetry of the crystal. And if I actually go through the sequence, I can see that the structure is evolving. I can see also contrast in these regions, for example, that correspond to the presence of precipitates with a different evaporation field. I can see here that this pattern is broken at a grain boundary. Here I can see the pattern from yet another grain with a different orientation. So there's actually quite a lot that can be gained from these types of analysis. And these types of patterning is not completely dissimilar to what we are maybe more used to seeing, the Kikuchi diffraction lines that we find in electron backscatter diffraction. The origin is the same somehow, that we are looking at crystals, but this is diffraction, so it's in the reciprocal space, whereas this is all in real space and is caused by the morphology and the faceting of the specimen surface and the resulting trajectory aberrations, which will be covered in a separate lecture. And this indeed, if we move back to the previous lecture on the field evaporation principles, the specimen will be faceted and will present the intersection of a spherical surface, a spherical cap, with the crystalline lattice forming this series of terraces with a different size and corresponding to different interspacings, basically. So different facets corresponding to different sets of atomic planes. And again, if we apply the voltage, the field distribution is revealed by field microscopy. We can see the similarities there, and here we can see that the field right at the edge of the terraces is higher, and this will cause some trajectory aberrations, pushing the atoms from these regions away from the center of the pole on the detector. And in a way, this is reflected on this pattern in the field microscopy. So if I look at different materials, for example, FCC materials, this is a O2 set of planes in pure nickel. This is a 111 pole or set of planes in pure gold. In BCC, you can see here two different 110 set of planes in pure tungsten and pure iron, so the material plays a role. If I look at the same specimen actually, but run in different conditions with the laser or high voltage pulsing at the same base temperature, I can see that the pattern is also quite different. So it will be, I'll get back to this afterwards, but it will be dependent on the analysis conditions. And that's just an HCP pattern just to, show how mind-boggling it can be, and it can get quite complicated to identify all of these different poles and sets of planes. So what causes the differences in the point density on the detector? It all relates to the local curvature of the specimen at the surface. And these might actually change with the temperature. So for example, this is a pure aluminium specimen. I can see a beautiful O2 set of planes here. The 111 is sitting down there. That's the 1220 set of planes, and 113. We can all identify those. When we build the reconstruction, we can typically image the planes there. But as I increase the temperature for the same specimen, I can see the pattern changing quite significantly, with a much denser area forming, for example, here around the O2 set of planes, or the O2 pole. And it only gets worse as the temperature gets higher, and some of the minor poles just simply disappear. At about 220K, I see this sort of wavy pattern. The O2 is still there somehow, and the main zone lines also still appear, but I would not really trust that data, because it means that locally we ended up with ions, atoms probably moving on the surface before the field evaporated to form this sort of wavy pattern there. Again, the specimen's shape depends on the temperature, so the experimental conditions. And we're going to build different radii over the cross-section of the specimen, where some set of planes, atomic planes, are sitting. And this can be explained because the work function and the bonding, the packing of the different sets of planes is simply different. For instance, Gongsha, when he was at the University of Sydney, did a series of experiments that was quite interesting. So he looked at using various laser powers, for example, and then start the run. And you could see that after some time we were field evaporating mostly with high density on one side, which is the side from which the laser was coming. And this can be explained because we heat the specimen specifically here, and if the heat conductivity of the sample is not high enough, then even during the pulse we are going to build a thermal gradient across the field of view. And so we end up with a flat region right on the side where the laser is coming. When we restart after this laser running pulsing run, when we restart the instrument, the evaporation mostly comes from that side, the other side, where the curvature is higher, where the field is higher. And then we couldn't do that successively from one with the different laser energies and different going back to the voltage pulsing, and we could see the pattern shifting from the region where the field was initially higher to a time where the evaporation was much more homogeneous across the field of view. So there's really a lot of information from these detector maps that can be important to interpret your data afterwards. Sometimes also right within AP Suite or IVAS, you can actually look at the way the pattern changes as you go through your experiments by just selecting a small slice of your data. In that case, there's very little change. You can just see, for example, here that the pole was well within the field of view, and here it's starting to reach the edge of the field of view. And there are many reasons for this, but basically as the specimen blunts, the compression of the ions might change ever so slightly in a way that the field of view is not exactly constant during a run. I revisited, for example, that dataset from colleagues from France, Fred Danois and Mohamed Gounet, And here there is an interface between ferrite and what used to be austenite that transformed into martensite. And at different points in the sequence of evaporation, I can see here a pole, a low density area. It's not hugely clear, but it's there. And as I go through the analysis, I can see this bright ring that is actually the interface between the two phases. And I've mentioned this before. The microstructural features typically affect the field evaporation behavior, so we could see more multiples at a grain boundary, for example. And here we see also that there is a dense region corresponding to an interface. And here we went from one grain to the other grain, and the position of the pole is actually almost the same because there is an orientation relationship between the two phases. You can see the pole, the interface is shrinking, and finally the other pole. Now, if I go through that one dataset from Allison, Kwiatkowski, da Silva, you can see I was in the first grain, the pattern was whatever it was. Second grain, the pattern is not completely dissimilar with a series of poles. And then as I reach the end there, I'm going into a third grain. And so here you can see these three poles, which are all 110s. The 111 pole is right there in the middle. I have now gone through the grain boundary, which is a low angle boundary. I'll get back to that. And now I'm in the bottom grain that has, after we've traveled through a high angle boundary. Again, quite a lot of information. So if I look through in more detail, here I have a first grain with a 111 pole right in the center. A second grain that has almost the same pattern forming, just slight shifts of the pole positions, which is indicative of a low angle boundary. And finally, a larger shift and some rotation of the pole here in the bottom grain. So we could actually retrieve the full crystallographic nature of the boundary from grain 1 to grain 2, and then from grain 2 to grain 3. And we could see that the first one only has about 5 degrees change in orientation, and from grain 2 to grain 3, it's over 10 degrees. Finally, just wanted to give you a hint also that sometimes by looking at the voltage curve and in correspondence the detector map, we can see that here in this analysis we have a nice mass spectrum and a nice detector map with poles and so on and so forth, and the voltage increases nicely and steadily. And then we have this massive jump in voltage. And here what I see is a pattern that's completely inhomogeneous. And the mass spectrum is all mostly noise and a bit messy. And yes, there's still a peak corresponding to maybe some aluminium that was in that sample. But mostly that data I cannot trust. And this was a sign that effectively there was a fracture during the analysis. We probably lost a whole chunk of the specimen, and that data set should probably only be analyzed up to about that point. Sometimes specimens reshape. So in that case, we're looking at a pure tungsten data set, and the voltage was increasing steadily. You can see that it's quite steep, so the specimen had a pretty large shank angle. And we can go from this map to that map after going through a fracture again. And we had, for example, this series of detector maps forming after a small chunk of the specimen was lost. The specimen progressively reshaped, and we end up in good field evaporation conditions again. What happened during the fracture is quite difficult to know, and there might be that there was heat exchanged when the sample fractured. So it might be that the microstructure actually was changed by this process. So again, whether you want to trust that data or not might be questionable. Right, to conclude, some things to bear in mind. Ion in the atom probe are collected by a position-sensitive detector. The detector is made of microchannel plates that convert an ion impact into millions of electrons, and these electrons are collected by a delay line, allowing to retrieve the impact position. The point density on the detector map reflects the local curvature, basically reflects the magnification and changes in the magnification. For many crystalline materials, there's a pattern that forms that corresponds to these sets of crystallographic planes. So once we can identify them, we can actually reveal aspects of the crystallography of the specimen. And it can sometimes be really quite informative when you know you wanted to go from one grain to another. You're looking at grain boundary analysis, for example, or interfaces. Then by looking at slice by slice, you might be able to spot what is happening at what point in time during your analysis. On this, I leave you, and hopefully you'll find this of interest. And if you have questions or want some more reading material, please feel free to ask. Bye.